All right, hey everyone. I'm going to be covering question 5, which is this tree method walkthrough. This is a really important step when we're analyzing this recursive code. If you kind of remember from the beginning of your section, we might have talked about like there's kind of 3 main steps to analyzing any type of recursive code, which is like transforming that recursive code into a code model that we can better understand like what's the runtime as we go to infinity. We have kind of 3 steps. The first step would be to take that code and turn it into a recurrence, which is something that looks like this. So we'll kind of assume that that's already been done. We have the recurrence already. If you want some more practice with that, there's another review video that's going from code to recurrence, which you can check out. And then now we have this kind of like beefy step of going from recurrence to a summation. I would say that this is probably like the most complex step, taking this recurrence and going to a summation. And then once you have that summation, it's much easier to transform that into a closed form, and then you can understand like what's the runtime as we go into infinity. But I would say that this is kind of like the beefiest step, going from recurrence to summation, and so we're going to kind of go through that here. This is the same problem that we went over in section, but it might still help to like watch somebody go over it again. So basically what we're going to do is we have this thing called the tree method. It's a little bit arbitrary in like how we draw this tree, but basically the goal is to help us like kind of find out like certain patterns from this recurrence and kind of like extrapolate those patterns to understand the like overall runtime. Because if you just looked at this, I don't know about you, but for me, I have kind of no intuitions about like what the runtime of this is going to be. Like, it's just really hard to figure out like, okay, I have like 3 recursive calls that I pass in n divided by 6 to, like, what's this going to look like? Like, how much work are we actually going to do? That's where the tree method comes in and helps us. So don't be too overwhelmed. In the end, we're going to get a summation, but like when we're doing the tree method, we just start off with like smaller questions and kind of build up to a larger question. So you can sort of see like, we're not going to answer these yet, but like you can see that we start off by saying like something smaller, like what's the size of the input at level I? Don't worry if you don't understand like what level I means or size of the input, but basically this is like a smaller question than like what's the, like if we go down here, you can see like, oh, like what's the expression for the total work? Like we're going to kind of like we're going to build this expression for a total amount of work up in small pieces. So yeah, before we dive into answering these questions, let's hop over to the slides. So yeah, this is problem 5, A through G. Again, these slides are also linked on the course website. Might be helpful to take a look at here. So if we ask you to use the tree method, the first thing that you should be thinking about and the first thing that you should do is start to draw a tree for this recurrence. What do I mean by draw a tree for this recurrence? Great question. So what we're going to do is each node in the tree is going to represent a recursive call. So for example, this recurrence is saying like, given any number n, this function a will take it, and if n is 1 or n is less than or equal to 1, it's just going to be 1 work. Otherwise, we're going to have some more recursive calls plus n amount of work. What we're going to do with this tree is that each node is going to be a recursive call, and what we're going to do is at first we're just going to assume that we kind of like start off with a big input. Like we don't hit the base case. We're always going to kind of go into this recursive case here. So we're going to assume that we always go into the recursive case, and what we're going to do with this node is we're going to put in what the input is to that node, the amount of non-recursive work. So this is like the work that this node would do if you don't count the other recursive calls, and that's what we're going to put inside as the work. And then for each recursive call that this node makes, we're going to draw in another node, right? Because remember, we're modeling each of these A calls as a node. So each A call is going to be a node. So if I basically have 3 A n divided by 6, we're going to make those like 3 separate other nodes in our tree. And we're going to keep doing the same thing over and over. So if we were starting off here, you can see that like, okay, if I was given an input of n, right? A takes in an n. How much non-recursive work are we going to do? In this case, we have a plus n right here. Right? That's this plus n is not recursive. I'm not like recursing. I'm not calling a any more times. So that's our non-recursive work. So it just happens to work out that the input and the work are the same for this one. But you can imagine like if this were an n squared, like plus n squared or plus anything else really, then the input would be n, but the work would be n squared. or the work would be kind of like whatever this term is here. But in this case, again, right, if I was given an n, I'm doing that amount of work here. So that's why we start off with this node, right? And so we have, the input, we have this like non-recursive work is what I'll call this. And now we need to kind of model this recursive work here. So we see that we have a 3a n divided by 6. So what we're going to do is we're going to make 3 new nodes, right? Because we have 3 calls to a of n divided by 6. And so for each of those 3 nodes, what we're going to do is our input here is going to be n divided by 6, right? Input is n divided by 6 because that's like what this says, right? I'm making 3 recursive calls with n divided by 6 as the parameter there. So the question is then, if I was given an input of n divided by 6, how much work is that node going to do? Well, the work is actually going to be n divided by 6, which might be a little bit confusing, but like the idea here is that this n can, like, you can really think of this as like any parameter. It's just saying like a is taking in a parameter, and I'm saying I'm going to make 3 calls to a with my parameter divided by 6 plus the parameter amount of non-recursive work, right? Like, n just refers to that parameter there, right? So in this case, if the parameter was n divided by 6, then my work done, this is n divided by 6, my work done is going to be n divided by 6. And I'm going to make 3 recursive calls with n divided by 6 divided by 6, which is the same thing as saying n divided by 36. So, hopefully you start to kind of see a pattern, but basically you always want to start drawing this tree. I usually draw 3 levels of the tree, but you can always draw more if you're not like starting to see these patterns. But for now, we'll just draw 3 levels of the tree. So you can see, okay, each of these nodes with an input of n divided by 6 spawns off 3 new nodes. And the input to those nodes is n divided by 36. Remember, because if I was given a parameter of n divided by 6, the calls that I'm making are going to be n divided by 6 divided by 6, which is the same thing as saying n divided by 36. So hopefully this starts to kind of make sense a little bit. Of course, feel free to like post questions about this. If you have them on Piazza, we'll definitely be free to answer them. But once you have this, now we can kind of like, okay, and by the way, so we're going to kind of keep doing this pattern over and over again, right? As you can see, like, given an input, I'm going to make 3 recursive calls with n divided by 6 plus n, blah, blah, blah. I'm going to keep doing that like probably a lot of times. But eventually we're going to hit a base case here. And, for right now, we just put in ... dots to handle all these recursive cases. But eventually, I'm going to basically be given an input where my input is 1. And what does this say? Well, if the input is less than or equal to 1, I'm going to do 1 work, and I'm not going to actually make any more recursive calls. I'm done, right? Like, that's the base case. I'm not recursing anymore. And so what we're going to do is we're going to say, okay, like, once we kind of reach something, when the input is 1, the work will just be 1. And, of course, like, I'm not going to spawn off any new nodes here. Right, so eventually we're going to get some last level of the tree that looks like this, where we give an input of 1, and the work is going to be 1 for that. Okay, so lots of kind of discussion about like how we draw this tree. Definitely feel free to ask if you have any questions about this, but hopefully it's making a little bit more sense how we got this tree from that recurrence. So now the nice thing is that once we have this tree, we don't really like we can kind of tree is modeling the amount of work that the total amount of work that recurrence is doing. So now what we're going to do is start answering those questions that we had in on the section handout, right? So the first question asks, okay, and they're asking questions about this tree, just mind you, right? So it's really important to be drawing this tree. So the first question asks, what is the size of the input at level I? Okay, so one more thing that we have to kind of clarify is it's talking about level I. So you might be kind of wondering, like, what does level I really mean? Well, what we're kind of thinking of here is like each like level, basically, it's like the first level 0. What we say is this like root node right here. Right? This is on level 0. It's kind of like 0 hops away from the top. Level 1, what we'll say is this level right here. Hopefully you can see my mouse on this recording. If not, that will be unfortunate. But it's that it's the level with all the input of n divided by 6. And we're saying that this level is like 1 hop away from the root. So we'll call that level 1. So arbitrarily, we just start the levels off at 0. and they kind of like represent like the number of hops that node is away from the root, right? So we have 3 nodes that are 1 hop away from the root. They're all on level 1. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes that are 2 hops away from the root. We'll call that level 2. And the root itself is level 0. And so these levels kind of like continue on. So if I wanted to know what's the size of the input at level I, what we're saying is, okay, at level 0, the size of the input is n, right? So we want an expression that says, okay, given level 0, I want my size of the input to be n. Given level 1, I want the size of the input to be n divided by 6, right? Because these are all n divided by 6. Given level 2, I want my input to be n divided by 36, and so on and so forth, right? We could kind of continue this and be looking at how this input changes. But I think with just 3 inputs, we can start to see a pattern, right? So you want where 0 corresponds to n, 1 corresponds to n divided by 6, 2 corresponds to n divided by 36. And what you might kind of notice here is that we're, and right now we kind of have to start to try to reason about a pattern here, right? So what's happening to the input for each level? Well, it looks like starts at n, then we divide by 6. Then we divide by 6 again, right? Like each input is kind of dividing the previous input by 6, which we could also sort of see from our recurrence, but like, I think we can see it visually with this tree as well. So what I would say is like each level, we're dividing by 6 one more time, right? So we're continually dividing by 6. So basically, we divide by 6 at each level. So the input at level I is n divided by 6 to the I, right? So the first level, right, 6 to the 0 is just 1. So I'm going to get n divided by 1, which is just n. Okay, works out. Okay, on level 1, we have n divided by 6. So n divided by 6 to the 1, that's true, right? Like that works out there. And then on level 2, we start to have like n divided by 36. And 36 is just 6 squared, right? And so we kind of see that these like the denominator here is just going to be like a power of 6 as we keep going down. If we went down another one, you'd see that like it's n divided by 6 to the 3rd. So this starts to work out. And this is like actually the pattern that we're seeing here. So just like a tip too, once you kind of come up with an expression that you think works, make sure to plug it in for these levels here and just make sure that it actually is working, right? Like, does it actually work for level 0? Will this actually give me an n if I plugged in 0 to this expression? In this case it does, right? I kind of walked through that. So just make sure to be like checking your work along the way and don't like never just like kind of guess at what this is. Like make sure it actually works with this small example here. Cool. So that's the input to the node at level I, right? And we can write down the answer to 5a would then be n divided by 6 to the I. And I'd write that down on my piece of paper and we'd be done there, right? So again, we're starting off with, it's not like a simple question, right? It's definitely kind of hard to reason about, but like, it's a question that can be reasoned about, right? Like, it starts off smaller like this and we'll start to kind of combine all this stuff into larger expressions. Okay. So now we say, what is the work done by a single node at the non-base case level I? So what this is saying is like, okay, given a node like this, the amount of work that it does is n, and I want an expression that gives me the amount of work a node does based on its level, right? So this work does this on level 0, I do n work. On level 1, I do n divided by 6 work. On level 2, I do n divided by 36 work. So looking at 5b, actually, the other thing we could look at is like the input and the work are always the same, right? The input and the work are always the same. So basically for 5b, it's just the exact same thing, right? Because the work per node is just the same as the input to a node. But again, only in this case, right? It might not always be the case that the work per node is equal to the input. So you have to be careful and make sure that you're actually coming up with an expression for the work. In this case, we can take a little bit of a shortcut because we're looking at the work and looking at the input, and they're the same. But you might have to do that same process that we did for the input to figure out what the work per node is in general. So on my piece of paper, I would write down, okay, n divided by 6 to the I. That's the answer for B. Okay, so for 5C, what's the number of nodes at level I? We're going to do the same sort of thing where we try to find a pattern. Okay, what is the number of nodes at level 0? Well, we have one node at level 0, right? No other nodes at level 0. No other nodes are 0 hops away here. Okay, so we have, okay, so if, I is 0, we want 3. Or sorry, if I is 0, we want 1. Excuse me, sorry about that. If I is 1, how many nodes do we have? 1, 2, 3. So if I is 1, we want an expression that gives us 3. If I is 2, we want an expression that gives us 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So, okay, I start off at I is 0. We have, we're going 1, then 3, then 9. If we did another one of these, you'd see that there's 27 of these arrows here. So just continuing on this pattern. So, what is the expression for the number of nodes on a level given I, right? The answer would be 3 to the I, right? Because, and yeah, the other way to kind of think about this is like each non-base case level, like each node is producing 3 more nodes. So we're kind of like multiplying by 3 each time we kind of go down these levels. But again, we can just do this by just counting, right? And just saying like, what's the pattern? We go 1, 3, 9. It looks like those are like powers of 3 basically, right? So I have, just, and again, right, let's check this expression. Does 3 to the 0, does that produce 1? Yes, 3 to the 0 is 1. Does 3 to the 1 produce 3, right? Because we need this to be equal to 3. Yes, it does, right? Does 3 to the 2 produce 9? Yes, it does, right? So we can be checking our expression along the way. But we have 3 to the I nodes at each level. Because I'm just counting, right? At level 0, we have 1. At level 1, we have 3, etc., etc. So I would write down on my piece of paper 3 to the I as the answer to C. Okay, so now we're going to get into maybe like a more, like a beefier question, I would say. What is the total, so if we're looking at 5D, what is the total work at the ith recursive level? So I want the total work, which is like, at level 0, we just have n work because we have one node that does n work. Okay, at level 1, we have 3 nodes that each do n divided by 6 work. So I would say it's like 3 times n divided by 6. In general, the total work at a level is just the number of nodes at that level times the amount of work per node. And, if only we had expressions to tell us what the number of nodes at a level I is and what the work done by a single node is at level I, well, we already have that, right? So in general, right, it's the total number of nodes in level I times the amount of work per node at that level. Hopefully that kind of makes sense, right? Like the total amount of work done at level 2 is just the work of an individual node, since all these nodes do the same amount of work. It's the amount of work of an individual node at that level times 9 basically, right? Because there's 9 copies of that node. So we can just plug in our expressions, right? We can plug in 5c here to get the number of nodes at level I, and then we can plug in 5b here for the work per node at level I. So that's kind of like why we ask those questions, is because now we can combine them. And this is the answer to D, right? It's just 3 to the I times n divided by 6 to the I. So I'd write that down on my piece of paper. So again, if we ask you for the total amount of work at the ith recursive level, we just combine the previous questions that we've been asking here. So yeah, hopefully that's making sense. Of course, I'd stop for questions, but this is just a video, so I can't. Okay, cool. So we're getting somewhere, right? Like we have basically for any level of the tree, we have basically the amount of work we do there. So we're almost done, but we still haven't kind of considered this, like, we have like one special level, and we've kind of highlighted it down here, which is that like base case level here. So the base case level, right? It's right now what we've been doing is kind of like modeling the amount of like recursive level, or like the recursive work, right? Because this only works, we've only been looking at these recursive levels, like the things at the top. But let's consider this base case level. It's kind of like a special case that we need to handle separately. So 5E asks, what is the last level of the tree? What is the last level of the tree? Well, we kind of start off at level 0 here, right? Then we go to level 1, has an input of n divided by 6. Level 2 has an input of n divided by 36. If we went back to this recurrence and we looked at this, well, how do we know when the base case is hit? It's when this input, right, whatever I give as input here, is less than or equal to 1. right? So the last level, sorry, let me go back here. The last level occurs when the input equals 1, right? Yeah, so again, right, sorry, we pulled up the recurrence again. We hit our base case when basically the input to the node is equal to 1. And we already have an expression for the input, right? 5a gave us that expression for the input of the node at level I. So what we're going to do is we're going to solve for I, right? We want to know what I, what level is it when we hit the base case. So I'm just going to set this expression, n divided by 6 to the I equal to 1, right? I want to know when the input is equal to 1. That's when I hit my base case. Hopefully making sense so far. So what we can do is we're just going to do some algebra here. The first thing that I'll do is kind of multiply each side by 6 to the I. So that gets rid of it in the denominator. And then now, this is maybe something that is like, rusty or you haven't seen much before. If you want to get rid of an exponent here, the way that I get rid of this 6 to the whatever is I can take the log base 6 of this. So log kind of cancels out exponentiation. It's kind of like the inverse of exponential is like a log. Like exponential is like you're multiplying by 6 each time. Logs like you're dividing by 6 each time. So I'm going to take the log of this side and the log of this side, and we'll get that. Now we just have I, right? Because I got rid of that 6 to the I by taking the log base 6. So we get that I is equal to log base 6 of n. That is our last level of the tree, right? Because that's when the input is equal to 1. So, sweet. So for 5e, I would write down log base 6 of n. And again, right, we're getting points for all this stuff, right? So, I is equal to log base 6 of n. The other way to kind of think about this is we're constantly log base 6 of n kind of says that's the way that you can interpret that is the number of times I have to divide n by 6 to get 1. And you can sort of see that each input is just dividing by 6. And so this really does represent the number of times I have to divide by 6 to get to 1. So anyway, that's the answer to 5e is log base 6 of n. Okay, so you might be wondering why did we do that? Well, okay, now we want to know what's the total amount of work done in the base case. Okay, so 5f is what's the total amount of work done in the base case. We want to know that. Again, we can do the same sort of thing that we were doing with the recursive cases, right? It's the total number of nodes in the base case level times the work per node in the base case level. So let's start to kind of decompose this expression. If I was looking at this and I was wondering which one is kind of easier to compute, let's start with the work per node in the base case level. If we looked at the base case level, the work per node is just 1, right? Because I'm just doing a constant amount of work, right? If I given an input of 1, I just do 1 work, right? So that's maybe an easier way to start here, is that the work per node in the base case level is just 1. So I would maybe write down 1 here. Okay, that only leads us to know what is the number of nodes in the base case level. And this is kind of another kind of tricky one. How do I know what the number of nodes is in the base case level? Well, what do we know? We know that the base case level is at log base 6 of n. And we also have an expression that tells us the number of nodes at any level in our tree, right? If we looked at 5c, we said that there are 3 to the I nodes on the ith level of this tree. And we also said that in 5e, the base case is on I equals log base 6 of n, that level. So what we can do is, so we have, 3 to the I times 1, because, it's 1 work per node, right? And our expression is 3 to the I for any level here. And we actually know exactly what the base case level is. So we can just plug in 3 to the log base 6 of n, right? Because it's 3 to the I in general, and we know that the special level, this special base case level, is on log base 6 of n. That's that level. So that is our answer to 5f. I would write that down on my note sheet. 3 to the log base 6 of n. You can include the times 1 or not if you want to. Cool. Okay, we've answered, a bunch of different questions. So now comes kind of this big question, which is, it says combine all the answers from the previous parts to get the total amount of work that's done here. Okay, so now we're gonna kind of move out of start to think about what do all these expressions that we have mean. Really the important expressions that I would say right now are kind of like 5D, which is that total amount of work at the ith recursive level, and 5F, which is like the total amount of work done in the base case. So if we really thought about like what's happening with this tree, well, we have kind of like recursive work going on where I starts at 0, then I goes to 1, then I goes to 2, and it kind of keeps going on and on and on until it reaches log base 6 of n. When I reaches log base 6 of n, we're just doing that base case amount of work. So really what we want to do is, and we already have the base case amount of work, so we want to kind of say, have an expression that says, okay, it's like the base case work, which is the answer to 5F, right? So it's just like the answer to 5F plus the total recursive work. Well, right now, all that we have is just the work done by a single level, but we want the work done by all levels. So what we're going to do is we're going to actually model this as a summation. So I kind of just flashed this slide at everyone, but don't worry, we're going to kind of decompose this. So the first thing that I want to start off with is this base case work, right? Notice here that I have this 3 to the log base 6 of n times 1. That comes from the fact that we have one base case level, right? We don't have multiple base case levels. We only have one base case level. And we already figured out that the work done at the base case level is this answer here. This is our answer from 5F, right? That is just the total amount of work done in the base case level. Okay, so we can kind of say like, okay, yeah, of course, every recursive tree is going to have at least one base case level. So now we want to know what's the total amount of work done by the recursive levels. Well, what we're going to do is we're going to say, okay, well, we know that given a recursive level I, right, we have this expression from 5D that says that this is the total amount of work for the ith recursive level, right? We just already came up with that in 5D. Now what we want to do is basically sum all of the recursive levels up, right? So remember the summation, we have like the starting and the ending bound, and each time I increments by 1. So we start at I equals 0, right, because we start at the root, right? Again, remember, we said this expression works for any level in our tree, starting from 0. So we start at 0, and we want to know, like, what's the last recursive level here? In general, it's like kind of hard to think about. Like, I don't know when this stops. Like, we did I equals 0, I equals 1, I equals 2, but when does it stop? Well, we can use the fact that, like, the last recursive level is just going to be the one level before the base case, right? If that kind of makes sense, right? Like, the level right before the base case would have been recursive because it would have spawned off these 3 nodes. But then we're done, right? We're not going to have any more recursive levels. So the top of our summation is log base 6 of n minus 1. Because we're saying go from 0 to the level right before the base case. All of these are recursive levels. And we said that the amount of work for any recursive level is this, right? So I should be able to make a summation that goes from 0 to the last recursive level that has the amount of work per level there, right? So really what this summation is doing is saying for each level, sum the amount of work on that level. And that should give us the total amount of work in this tree, right? If I took each level and summed the work from that level, then I basically get at the end, basically I have this sum of all the recursive levels here, plus the base case level here. So I get the total amount of work, right? I've summed basically all the recursive levels plus the base case level. And this is our final summation. So this is where I'll end this part of it, because now we can take the summation and turn it into a closed form if we want. But this is what we're expecting on these like tree method-like problems. And this is how you get to this final answer, right? If I just gave you this final answer right away, like nobody would kind of know what's going on, right? It's pretty complex. But hopefully you can kind of see like how we build this up kind of in smaller steps to get this like final summation. If you have any questions, feel free to post them on Piazza. We'll definitely be checking there. And good luck with your next assignment and the midterm.